Hello, another example problem. This time it's 9.15. It says here a wood beam supports the load shown, and the cross-sectional dimensions are also shown, and we're just asked to determine the magnitude and location for the maximum horizontal shear stress and the maximum tension bending stress. Okay, so our member here, simply supported timber beam with a distributive load and then a point load, and then our two supports. Cross-sectional area here, as you can see, it's a composite material. We have two pieces of wood, two different types of pieces of wood. So we'll have a moment of inertia that's going to be, our moment of inertia, I sub z, is going to be the moment of inertia of the bigger piece plus 2 times the moment of inertia of one of the smaller pieces. Okay? So what I've done, the first step that you should do, and I've already done it, is go through and draw your diagram or a free body diagram, determine your external reactions, and then draw your shear and moment diagrams. And the purpose from this is so that we can see what the maximum shear is going to be, right? And the maximum moment, what it will be. Okay? So the next thing that we can do is solve or determine what our moment of inertia is going to be. So over here I'll say my moment of inertia is then going to be from the dimensions shown, the bigger piece, which is going to be 75 millimeters multiplied to the height of it, which is 240 millimeters, quantity cubed divided by 12 plus 2 times base is 20 millimeters, height is 100. So 2 times 20 millimeters, 100 millimeters cubed divided by 12. So we get I sub z, which equals 89733 millimeters to the fourth. Okay? So for part A, our max shear stress at the neutral axis, right? So neutral axis, what we need to do when we look at our neutral axis here, we're going to say this halfway point, right? We're going to have to sum the areas, right? What's our Q? Our Q value going to be? Well, our Q value is going to be the whole area, right? So this whole area. So Q will equal 75 millimeters multiplied to 120 millimeters, because that's 240 divided by 2, multiplied to 60 millimeters, because that would be the Y bar of this main piece, and then add 2 multiplied to 20 millimeters multiplied to 50, which is half of 100, and then the Y bar would be 25. Or not Y bar, but Y sub I. Okay, so the Q value for the first portion is going to be 590,000 millimeters cubed. Okay, so coming back, sorry, I'm kind of jumping around here. So our max shear stress, so tau max, is going to equal QV over IT. Okay? So the Q we've just determined is going to be that 590,000, right? So 590,123. Our shear max, right, is going to be 9.54 kilonewtons. We'll just turn that into 9,540 newtons. And our moment of inertia, which we've already determined, 897,333 And then the thickness. Now this could be a little bit confusing, but the thickness, what is it going to be? Well, it's going to be the summation, so 20, 40, and plus our 75 here. So the whole thickness of this, which will be 115 millimeters, right? So you then should get a shear stress max to equal our 545. We'll just do our units. If you can follow me through here, is kPa. Okay. So that's our shear max. So the shear stress, and we'll do the top edge of the cover plates. Okay. So the cover plates, there's going to be at the top edge here, this distance here. So now we need the area of this, a new Q. So our Q, we'll call this Q sub 2, the new one, is going to be 75 multiplied to 70 multiplied to 85. Okay, and then this would be 446,250, and that's millimeters cubed. Okay, and if you're confused on these units, just it's the thickness of this piece here, right? The big middle piece. Let me just do a green box. So we're analyzing this section, right? So it's this distance here is 75 millimeters. The area is 70 times 75, and then our distance from here to the neutral axis would be 85. Okay. So we take that Q value, and let me go back over here to where I was working before and say our Q, or I guess our shear at those points, right, is going to equal VQ over IT, which is going to equal, again, our 9,540 newtons multiplied to that Q value that I just determined, which is 446,250, 446,250, and divided by our moment of inertia, which again is 897,333. 1, 2, 3, 3. Too many threes. Okay, and then the thickness, which is going to be just 75, because we're only analyzing that one portion, the middle piece. And so this should give us a value of 633 kilopascals, right? Which is larger. So determining the larger value between these two, right? And so it asks, the problem statement was, what's the maximum shear stress in the beam? Well, it's going to be the larger of these two. So our tau max, I shouldn't have called this one tau max because it was just tau. So tau max for the entire beam is going to be then our 633 kilopascals. Okay, that's part A. So part B, let's read what part B was. Maximum tension bending stress in the beam. Okay, so max tension bending stress, so if you remember, so our bending stress is going to equal my over I, right? And the maximum moment, right, is 6.49 kilonewtons per meters, kilonewton meters. So our y distance will be the furthest y from our neutral axis, right? So 120 millimeters. So our stress sub B is going to equal we'll just say 6,490 Newton meters multiplied to 1,000 millimeters per meter, and then 120 millimeters divided by our moment of inertia, which is 8, 9, 7, and a bunch of 3s. 8, 9, 7, 3, 3, 3, 3, 3 millimeters to the fourth. And I didn't calculate this yet, so 6490 multiplied to 1,000 multiplied to 120 divided by 897, 1, 2, 3, 1, 2. So I get a max bending stress of bending stress equals 8.679 kPa. And that should be the answer.